And hello, Math 141 enthusiasts. So here we are in the final section of Chapter 3, Section 10 on linear approximations and differentials. So the first bullet states that the first part of the section has us considering how tangent lines can be used to approximate a function close to the point of tangency. Now we've spent all of our time dealing with tangent lines because the slope of the tangent line represents the slope of the curve, and the slope of the curve gives the value of the derivative of the function at that point. Well, a tangent line is a linear function, and what's interesting is that we can use the equation of the tangent line to approximate a function's value in a very small window containing the point of tangency. Now, that's so significant because a long time ago in a land far, far away, before technology was invented, sometimes coming up with exact values of functions was very difficult. But utilizing, in essence, a polynomial function, linear functions are first-degree polynomials, we can use that equation to approximate function values. So here's what I'm talking about in this picture right here. Okay, here's f of x. And let's say we select a point on the graph right about here. That's when x is equal to a. And let's say we draw the line that is tangent to the graph at that point. And I'm going to call this L of x. Okay, so basically what we're going to do is we're going to take the equation of the tangent line and transform it, basically make it look more function-like, if you will, utilizing function symbols. So we use point slope form, y minus y1 equals m times the quantity x minus x sub 1. So remember that m is the slope of a line, x sub 1, y sub 1 are the coordinates of a point on the line. So the only point we have is the point of tangency. And so the coordinates of that point are a and f of a. So f of a is y sub 1 and a is x sub 1. So we have y minus f of a equals m times the quantity x minus a. Now for the slope of this particular function, of course, that's the value of the derivative of f when x equals a, hence f prime of a. So y minus f of a is equal to f prime of a multiplied by the quantity x minus a. Now if I take this equation and solve it for y, by adding f of a to both sides, y is equal to f of a plus f prime of a multiplied by the quantity x minus a. So what we're now going to do is replace y with L of x, because y and L of x mean the same thing. So the function L of x is equal to f of a plus f prime of a multiplied by the quantity x minus a is called the linear approximation of f when x is equal to a. So what that means is in a very small window containing the point of tangency, the linear function f of x very closely approximates the function f of x. Now, you have to be in a very small window because the further you move away from the point of tangency, the further apart the linear function gets from the actual function, and therefore the linear approximation isn't as good. Now, we call this a linear approximation because we are using a linear function to do the approximating for us. In Calc 2, we expand on this because in theory, we can use any degree polynomial to approximate a function. So you can utilize a quadratic approximation or a cubic approximation and so forth. We actually call all of those polynomials Taylor polynomials, which leads us into Taylor's series, but that's going to be coming up in Calc 2. This is the beginnings of that, okay? The use of a linear function, the first degree polynomial, to approximate a function. So, whoops, what did I just do? I brought the, what's that called, a doc? I brought that up at the bottom. All right, so here's an example of showing how this works. So estimating the square root of the quantity 16.02. Now, nowadays, of course, all we would have to do is on our calculators is plug in the square root of 16.02, and at least to 9 decimal places, 4.00249919. That is an approximation, of course. Would have to be somewhere between the square root of 16 and the square root of 25, so somewhere between 4 and 5. Okay, but back in the day, before technology was invented, finding the square root by hand was not a fun prospect. So if we could identify the function that was being used and the point of tangency, we could come up with the linear approximation and use that equation to approximate the square root of 16.02. So let's show you how it's done. So the function is the square root function because that's what we're doing here. We're taking the square root of x. Now, x is not, in this case, 16.02. Well, that's the actual value of x. What we need is the value of a, and a is the x-coordinate of the point of tangency that the linear function's graph passes through. And it has to be relatively close to the value of x that you're using. So 16 is very close to 16.02. So I think it makes sense that having the tangent line through x equals 16 would be logical to use here. So then f of a, of course, would be f of 16, which is the square root of 16, which is 4. Okay. Now for the slope, we need f prime of x. So using the power rule, 1/2 x to the negative 1/2, which with a positive exponent is 1/2 square root of x. So f prime of a would of course be f prime of 16, which would be 1/2 square root of 16. Square root of 16 is 4, and 4 times 2 is 8, so the slope of the line is 1/8. So the tangent line, the linear approximation that we will use to determine an approximate value for 16.02 is L of x is equal to f of a, which is 4, plus f prime of a, which is 1/8, multiplied by the quantity x minus 16. That's not the equation of the function, that's the equation of the line tangent to the square root of x when x is equal to 16. So if we wanted to approximate the square root of 16.02, well, the exact value, that's the value of f at 16.02. Using the linear approximation, f of 16.02 is approximately the value of the linear function at when x is 16.02. So L of 16.02 is equal to 4 plus 1/8 multiplied by 16.02 minus 16. Now, if you wanted to finish this, 4 plus 1/8 multiplied by 0.02, and 0.02 divided by 8 is 0.0025. So when we add 4.0025. So the square root of 16.02 is approximately 4.0025. And when you compare that to the actual value up here that we used our calculators to get, it's pretty darn close, and close enough that we could say that, reasonably speaking, that that's the square root of 16.02. So the reason that polynomials are used is because polynomials are the easiest functions to work with, really regardless of degree. So that's an example of utilizing a linear approximation, okay, to approximate a function near a point of tangency. Now, the second part of the notes here is on this thing called differentials. Now, differentials, there's that shake and bake that I was telling you about in the other video. So the ideas behind linear approximation are often referred to in terms of the language of differentials. So when you might remember we talked about dy dx. So dy dx was Leibniz notation for the derivative of y with respect to x. Separately, and Bella is, if you can hear that, she's scraping on my rug. dy and dx separately, those are called differentials, and they basically represent approximations for the change in y and the change in x. Now, a long time ago, derivatives themselves were defined using differentials, and I did find a really good thing online that describes what differentials were and what they were used for. They don't seem to be used as much anymore because now derivatives are defined using limits. So, but here is rather interesting thing to take a look at. So in another picture, to illustrate what I'm talking about, okay, so if somewhere on the graph of f of x we select a point, let's say we pick this point right here, and we draw the line, see if I can move this a little bit, we draw the line tangent to the curve at that point. And where did my thing go? Hello, let's try this again. Okay, it's back. I hate it when that happens. Okay, so there is the equation, there's a tangent line, okay, through that point. So now let's say we wanted to pick a second point on the graph of f of x, let's say here. Okay, so here is the horizontal distance that we'd have to move to get to that point, and here is the vertical distance that we'd have to move to get to that point. So the horizontal distance, that's the change in x between the x-coordinate that we started at and the x-coordinate at this new point. And then the vertical distance, that of course is delta y, that's the change in y, the change from the y-coordinate of the original point to the y-coordinate of this new point. So now, if we took the approximate point of the second guy on the graph of the tangent line, right there, okay? So this blue point is approximately the same as this pink point right here, all right? If we were to take a look at this horizontal distance and this vertical distance, so I'm using blue to highlight that, okay? In terms of the tangent line, the horizontal distance is denoted as dx, and the vertical distance is denoted as dy. So when we take a look at this, okay, now delta x and dx, they're the same, okay, that distance is identical, but delta y is approximated by dy. So the change in x is the same, it's the change in y that is approximated. And so dy and dx are what we call differentials because they show us approximate changes in both x and y. So what's really neat when you look at this is that in general, when f is differentiable, then dx and dy are differentials of f, and dy is equal to f prime of x dx. So that really doesn't, it's not a profound thing because we know that dy dx and f prime of x mean the same thing. But if we treat dy dx and f prime of x as independent entities and we multiply on both sides by dx, we then get dy is equal to f prime of x dx. And since dy approximates delta y, it is going to be true that delta y is approximately equal to f prime of x multiplied by dx. So the change in y is approximately the slope of the line tangent to the curve through the original point multiplied by the change in x. So as far as this section goes, the big thing that you need to be familiar with is the concept of linear approximations, because being able to utilize the equation of the tangent line to approximate the value of the function is going to be very important. Differentials, I'm not going to spend really any more time on it than I've already done. So that is the end of chapter 3. Woohoo! And so from here, obviously, we go on to chapter 4. And in chapter 4, which is where we're going to see some applications of the derivative and where the derivative can be used. So we've laid the groundwork. You have the skills now for finding the equations and the formulas for derivatives. Now we're going to see where the derivative is really used, what it's used for. And we will see you at the beginning of chapter 4.